for example, when we come in here and we say, export Pinecone index is going to be Zach test, for example, if this index doesn't exist when the reference architecture initially stands up, it will create it. And if it does exist, it will not conflict with it or throw any errors about the fact that it already exists. So you can either create it here manually, as we're going to do just for the purposes of showing. But if you don't do that and you attempt to run the reference architecture after setting up the correct environment variables, and as long as you have valid API keys, then the reference architecture's front-end microservice will actually spin up this index if it doesn't already find it. So for the purposes of this, let's just call it Zach test. I happen to know that the front-end and the other microservices as well for this reference architecture are using 384 dimensions. And in order to just keep things simple, I'm going to stick with just S1 and create one index. So now that we have this first index provisioned, I'm going to come into here, which is my local clone of the reference architecture. You might have a different name for your repo, but this is the same repository that is here and that is fully open source. I just cloned it here earlier. And so the first thing I'm going to do is export my first required environment variable, which is going to be Pinecone index. And we'll call it Zach test, just as we did here. The next piece of data I need is this environment value. So this is the Pinecone environment. And then finally, I need my API key. So you come over in the left rail to API keys, grab your API key, and then that gets exported as Pinecone API key. The other thing to note is that if you were to forget to, say, export your Pinecone index environment variable and then attempt to run Pulumi up here, we do have code that is in this utils function, and it will check for required environment variables, and it would throw an error and tell you which one's missing. But at this point, these are the only 3 environment variables that you actually need to set to get started. And so at this point, we close out this credentials file, and we can run. The first thing that we need to do before we actually deploy and try to run Pulumi up is we need to initialize a new stack. So in Pulumi, a stack is a logical grouping of all the resources that we're going to deploy for this particular reference architecture, along with the configuration. And the stack infrastructure is kind of nice because it actually is maintained partly through the Pulumi cloud backend, and it allows you to sort of just move between machines a little bit easier as well. So we're going to do Pulumi stack init, and we can just say Pulumi stack init, and then the name, the arbitrary name that you want. So we'll just say deploy demo. Okay, now that we've created a new stack, which we can verify by running Pulumi stack ls, we can see that we are on the deploy demo stack right here. There are no resources. We haven't deployed it yet. And so now in this new stack, because configuration is separate, I need to run Pulumi Pulumi config set AWS profile Pulumi. And now we can run Pulumi up. And so now Pulumi is looking into our AWS account, and it's asking, do any of these resources that are defined in the index.ts file already exist? It's asking via the API, doing lists and reads, and indeed none of them exist. And so what we get is that we're going to attempt to create the entire reference architecture, start to finish, and that comprises 93 resources. So you could either say, no, I don't want to do this now. You could look at the details, or you can say yes. And to kick this off, we'll just say yes, and we'll start. Typically speaking, the reference architecture is pretty likely to come up cleanly in one shot. Everything is defined as code, including the Docker files and the Docker build processes for all 3 of the microservices. So now you'll see that that Pulumi is actually performing the Docker builds, pushing those images up to ECR, and then even handling for us under the hood the authentication, so that we don't need to actually worry about that. You don't need to do any manual Docker building. Everything is handled via code, which is really nice because it makes it easier to tear down as well, which we'll see later. So Also, typically speaking, at the time of this recording, this current iteration of the reference architecture takes about 17.5 minutes to come up from scratch. And that's partly just due to there's a couple resources, particularly the NAT gateways, of which there's 3 in the custom VPC. Those each take several minutes to provision, as does the RDS instance that is central to the central database that kind of coordinates the functionality of the whole system. That RDS instances also take a while to come up. So all told, we'll probably be, waiting here for about 17.5 minutes. So if you've gotten to this point and things are creating smoothly like so, then you can also feel free to walk away, get a coffee, stretch, go outside, touch some grass, and come back in 15 or 20 minutes. And so as we wait here for some of these things to provision, so everything's coming up, the custom VPC, the various auto-scaling policies, the SQS queue itself, load balancer, now the database and its own security group. Might be nice to just quickly talk through this architecture and what we're actually deploying. So what this reference architecture comprises is a front-end microservice. So this front-end microservice exposes a table UI that's built in React and Next.js to end users. And that allows users to perform semantic search by querying. They can also live edit any of the records in the table. Editing the records in the table is what causes the front end to issue SQL queries to Postgres. And when Postgres has a change, it emits that using PG notify. The Pelican microservice is listening to Postgres directly. When it gets changed records off Postgres, it places them on the SQS jobs queue. The separate microservice emu for embeddings and upsertings is listening, also pulling from that same SQS job queue. And as soon as it gets jobs, it converts the description of the product to an embedding and then upserts that embedding to the Pinecone index along with metadata that ties that vector back to the Postgres record. So for example, the metadata contains ID equals 11093 if the Postgres record ID was 11093. And so that is how we can actually maintain an end-to-end from front end all the way through the database, 2 databases, database, and then vector database synchronization. So as soon as a user edits a product description, that goes all the way through the system and gets embedded and then upserted into Pinecone, but with metadata that attaches it back to the original Postgres record. And that's how when users are searching in the front end, if they issue a query such as products with AI or products that help me clean my floor, whatever the case may be, then they're getting back the exact same view of the data that's consistent throughout the system. They're also able to, we in code, we go from the Pinecone results that were queried based off the natural language or the ambiguous natural language query that the user sent in, so the query vectors. And then what comes back in the results, the matches for those query vectors, includes the metadata that has all of the actual Postgres IDs. And then we're able to just directly select on those Postgres IDs in order to get back the data that we want to display in the UI. Okay, so still waiting here. Looks like just about everything on the supporting resource side, so queue, DB subnet, security groups is up, and now we're actually starting to provision the emu service. The RDS instance is about halfway through provisioning. If we come in here and look at our ECS panel in the AWS dashboard, we should now see clusters. And yep, indeed, we do see this cluster. So there's the Pelican cluster, the front end cluster, the emu cluster, and there's one service now provisioned for emu. And we are pretty soon going to attach, we've got the policies for the service, the actual IAM resources that allow emu to do the jobs that it needs to do, to read from the SQS queue, for example. And then pretty soon we should see the ECS service coming up and starting to spin up separate emu workers. So then those will all be here as well. Yep, and so now we've got 2 pending. So the emu service itself is performing a deployment within ECS to bring the